This video is solely made for me and myself only because the work that I used to do in during my research tenure, I gave a research proposal seminar, and after few months, I have left my PhD program due to some certain reason. Maybe I can disclose those reasons which are really personal to me only. Still, I can share with you guys. So today I'll give a seminar about my research proposal that I gave during my PhD tenure. So I hope you will really like if you go through the video till end to have an crisp or to have an idea of what is experimental research is on thin films, what other different fields people work on. You will have an idea about this video. This is the second time actually I'm just recording video, and I just realized after giving the talk I have not turned on the recording in my phone. So let us give it a try one more time. So this was the title of my talk: Boron doped diamond as a granular superconductor and the effect of granularity on superconducting transition temperature. So I used to work in lab grown diamond, especially on superconductivity and granularity. So this was the lab I used to work on, Material Science Research Center at Indian Institute of Technology, Madras. So these are the contents of my talk. I will give an introduction about the properties of diamond, various techniques on diamond thin film board, and a historical roadmap how actually you can grow diamond in lab. Then I will slowly give the growth kinetics, then various dependence of morphology on growth parameters, then the doping on superconductivity, how it was achieved in diamond, and boron doped diamond as a superconductor, granularity and its importance in applications. I will give some literature size survey where I will discuss about the effect of granularity on the superconductivity in boron doped diamond sample and the scientific motivation behind my work, the work done so far, and my future plans. So this evolves around the growth kinetics, exploring ultra nanocrystalline diamond and the effect of granularity on superconducting transition temperature. So as you know, diamond is a very precious gemstone. It is used in jewelry, but because of the exotic, some physical the properties of the diamond, it is a potential candidate for applications is machining in cutting tools because of the hardness of the diamond. You have a long lasting in your machinery parts. It is a good thermal conductor. It is also a good optical material. It is used in quantum devices and in electronics as well. So here is a phase diagram of the pressure versus temperature. So as you know that diamond is mined, actually it was first mined in India, and diamond in naturally can be grown. It is about 100 to 150 kilometer from the earth surface where the temperature and pressure is really high, and where in the lab the high pressure high temperature synthesis techniques basically mimics the nature, and with this you can grow diamond. But there was a sort of motivation: can we grow these diamond thin films in the lower region of the spacer, that where the chemical vapor deposition technique comes into play, where with a suitable substrate temperature with a lower pressure you can really achieve diamond in the lab environment. So what makes diamond fascinating is the high band gap of diamond because it makes it insulating. But with certain dopant in the diamonds lattice, you can make it semiconducting, you can make it superconducting. Diamond also has some unique properties like high hardness, which is obviously make it useful for the machining and cutting tools. It has also high thermal conductivity of 2000 watt per meter per Kelvin, which is really high, maybe lower than your graphene, but it is quite high compared to the other available materials. It has also high breakdown field of 20 megavolt per centimeter. It has high carrier mobility, and also it has high acoustic wave velocity. Because of these exotic properties, diamond can be used in electronics. See, in our modern days, we use silicon chips as p-type and n-type dopant. But in high power electronics, where the heat dissipation ratio affects the performance of the circuit. So because of that, you need a potential candidate or material which can radiate the heat so easily because of this high thermal conductivity. So that their diamond can really replace the silicon if we achieve p-type and good n-type superconductivity in diamond. So this is basically the diamond structure where diamond are sp2 bonded and it is in a tetragonal structure. You can see these are the carbon atoms which are bonded tetragonally in the diamond lattice. This is the unit cell of the diamond lattice structure. This is possesses a diamond cubic crystal structures and this belongs to this space group. It has a density of 3.52 gram per centimeter cube and it has a lattice constant that is the interatomic spacing of 3.57 angstrom. So different morphologies of diamond if we talk about we have diamond like carbon, we have ultra nanocrystalline diamond where the grain size is order of 10 nanometer. We have nanocrystalline diamond and these all are well advanced in the literature, well explored in the literature. We have microcrystalline diamond 100 nanometer to 5 micrometer. We can have some oriented growth depending on the certain physical parameters in our growth chamber and we can also achieve a single crystalline diamond. So these are the corresponding morphologies of those nomenclatures. If you go to microcrystalline diamond to nanocrystalline diamond, you can see the grain size is really decreasing. So in our lab, basically we use two type of technique. One is hot filament chemical vapor deposition, another is microwave plasma chemical vapor deposition technique. So we use methane as a source of carbon to grow the diamond. We'll have couple of hot filaments. In our case, almost 31 to 32 filaments were there. We'll let the gas flow into the chamber and we'll have substrate. We'll heat the filament and under some certain condition we can have diamond thin clips. The same scenario is mimicked in the microwave plasma as well, but it gives you more cleaner environment. Basically, in hot filament CVD, because of the metallic contamination that cannot be avoided during the growth from the tungsten filaments. Those difficulty you can really expel in the microwave plasma CVD process. But this CVD is a cheaper technique to have a polycrystalline diamond. So going back to the history roadmap, the scientists have actually wanted to grow diamond at a lower pressure environment because higher pressure environment is a high cost machinery restriction that is also cost effective. So we know that diamond is grown 150 to 200 kilometer below the earth's surface where the pressure and temperature is really high and makes the thermodynamically favorable situation for the diamond to grow naturally. But what happens in the history is 1950 this group they first had to synthesize diamond mimicking the natural growth condition of the earth. You use high pressure and high temperature and you have some carbon precursors. Basically if you pressurize it at high temperature then you will have diamond. In 1960s this group they developed chemical deposition technique, then so on then chemical vapor deposition technique people first realized the importance of hydrogen gas in the growth in environment and the works goes on and people tried more sophisticated technique like hot filament CBD which was in 1982 by this Japanese group. Basically Russian and Japanese they are experts in growing this lab grown diamond. And in finally 1983, 1986, people use MPCBD, more cleaner environment and faster growth in a chemical vapor deposition technique. So this MPCBD was technique was invented in 1983 and 1986. So now going to the growth of the diamond in CBD, growth kinetics and dependence of morphology on growth parameters. So this is basically a top view of the hot filament chamber which, when the lid was open. And we can see various quartz crystals to have a uniform distribution in the chamber. We have some couple of filaments, 30 to 31 filaments was there. Basically you put the substrate below this heated filament, and before actually growing the diamond you need to seed the substrate. In our case we used to use silicon as a substrate, and on top of that you will ultrasonicate the diamond samples in a diamond slurry solution, basically diamond small particles mixed in ethanol solution, and if we ultrasonicate this small diamond particles will settle in the top of the substrate. So this act as a nucleation center. For the diamond to grow, you need a material which has a diamond-like structure. So this is nothing but the nano diamond on top of the other substrate. So it is actually easy to grow diamond on top of diamond substrate, but if you for other substrate, you need to have initial seeding. Basically, you need to scratch the substrate by some diamond powder, or there is wet seeding while you use diamond solution in an ethanol mix environment. So this is a chamber. You allow the gas hydrogen and methane to flow into the chamber after you achieve some certain flow rate. Then you heat the filament at more than 2200 degrees Celsius. Then the atoms in the hydrogen will be stripped out, because this will be atomic hydrogen and it is very reactive with the methane. So then the chain reaction will happen with the methane that I'll also discuss. So this methane actually also the structure of diamond. So it is easy to use methane as a gas precursor for a carbon source for the growth of diamond. So this is the growth chemistry. We have decomposition of hydrogen. Hydrogen will be thermally activated and it will give atomic hydrogen. This atomic hydrogen will react with methane. Then methane will be produced, and in the process, this hydrogen atom can also bond with another hydrogen to again to give the hydrogen gas, and it may be flowed out of the chamber. And the reaction of the top layer of the diamond seed. So if you have a seeding particles which are tetragonally bonded carbon, but if there are some vacant places or loosely bound atom where there are some defects from the tetragonal bonding, one carbon is missing, then the carbon that is sourced from the methane gas will attack these places, then it will complete the tetragonal structure and a diamond will be produced. So this is called the H abstraction. From the tetragonal structure, hydrogen will attach, then another hydrogen will attach with this and basically makes it a vacant place for the carbon atom to settle in. So these are the chain reaction, step by step. Hydrogen is attacking the surface, then there is a vacant place and CH3 can be clipped in, and then another side again the same process goes on, then CH3 again will be clipped in, then another hydrogen will attack with methane, then there will be radicals like CH3 to CH2 to CH and C reduction. So finally what will be there in the structure is leftover carbon in the tetragonal structure. So then this is nothing but a diamond structure, so you can grow diamond thin films. So because of this hydrogen, you can achieve actually fast growth rate, and this hydrogen actually basically etch out the graphitic surfaces and helps in diamond growth at a lower pressure. So the main parameter which affects the morphology of the diamond thin films is the methane concentration, and one is the chamber pressure. So this is basically if you increase the methane concentration, your grain size of the film decreases, and if you decrease the chamber pressure as well, your grain size decreases, and this is well established. So if you use this condition, if you have a methane to hydrogen ratio of 1 to 2% in a chamber pressure of 10 to 50 torr, then you have microcrystalline diamond where the grain size is few micrometer, 0.5 to 1 micrometer or 20-30 micrometer as well in best cases. You have nanocrystalline diamond where the grain size are few hundreds of nanometer. But once you hit 4.5 to 5% of methane concentration and at a chamber pressure of 7 to 6 torr, then you will achieve ultra nanocrystalline diamond. So this work was done by one of our lab senior, where actually during the growth, basically in the recipe there is a program where actually you put hydrogen flow, you put methane flow for certain time, for certain pressure, and after some time if you change those concentration of methane to hydrogen ratio and the chamber pressure, then you can have a transition from microcrystalline diamond to nanocrystalline diamond. That is what is being shown here. You can see as the methane concentration is 4% and the chamber pressure is close to 30 torr, then you can see the chamber pressure is dropping and the methane concentration is increasing. Then you can have a transition from microcrystalline diamond to nanocrystalline diamond. So this is a integrated with a transition layer. Now morphology of the film on the growth parameters, especially stage for concentration or chamber pressure. So to understand the mechanism, we'll have an mechanism called a Vander drift mechanism. Basically, what happens? These are the diamond particles on the top of your substrate. When the chemical reaction starts, all the carbon atoms from the methane try to hit the top surface of the seed diamond particles. Then the diamond growth starts. Now, if this basically these seeding particles are the nucleation site. Nucleation site means from where the diamond will start to grow. More close the nucleation site, there will be competition of the adjacent columns of the diamond to grow in a particular direction. So if it is more congested, then the columnar structure will reduce like this. So here the methane concentration was less, so the nucleation density was low. But if you want to achieve higher nucleation density, then your columnar structure slowly breaks and you have more lower grains of diamond structure in your field. And if you increase the more methane concentration, you will see UNCD. So actually the effect of pressure is much less than the compared to the methane concentration. I will say the methane concentration plays the most crucial role and the filament temperature in sustaining this morphology. Now people have also shown the effect of chamber pressure. As you can see, they have used the growth from 0.25 kilopascal to 5 kilopascal, and at higher pressure they have seen that uh, the growth kinetic actually changes. At higher pressure you have much higher order grains. And from the excited diffraction pattern, it is also much visible. If you have a high intensity peak, that means the density of diamond is actually high. As you go to the nano regime, your X-ray peak broadens, and this really indicates that nano crystalline diamond peaking in your sample. So the thumb rule is you increase in the pressure of the methane, you have a higher granularity, that is lower grains in your sample. And if you increase in crystalline sizes, if you increase the sorry, this is wrong actually. If you increase the methane concentration, there will be a decrease in crystalline sizes. This needs to be corrected. Okay. So if you increase the methane concentration, basically your nucleation site will come close to together, then it will break the column and growth of the diamond growth. Okay. So keeping in mind, my works focus on the ultrananocrystalline diamond, which was achieved or which was established, but my plan was defined with the sample. So talking about the various dopants in diamond, so as you know, diamond is an insulator because of the higher band gap of 5.49 electron volt. This is a huge band gap. You just can't imagine how huge it is to make it an insulator. But if you dope the diamond with boron, then it makes it p-type. Basically, boron forms an donor level on top of the valence band at around 0.37 electron volt. And also there are reports of n-type doping in diamond, which is mostly done using phosphorus and nitrogen, but those n-type conductivity is achieved in the higher temperature. Because as you see from this band diagram, this donor level, this is actually far below the conduction band. So at thermal temperature, it is not possible for the electrons to overcome this gap and to come into the conduction band. So this n-type conductivity may be achieved in a higher temperature, but seems difficult at room temperature. So among these are the substitutional donor in the diamond, and lithium and sodium goes into the interstitial phases. So this work was done from one of my senior, Dinesh Kumar, and he has done some fantastic work. So he actually slowly increased the boron concentration, and he has measure the superconducting transition temperature for various sample, and he has shown at a critical concentration your Tc is high, but if you increase the more boron concentration, increase of Tc increasing, because literature says if you increase the boron concentration then your Tc will be high, but after some critical concentration again Tc will come to lower side, and this is pretty much familiar with other superconductor as well. So far highest reported Tc on single crystalline diamond is 10.2 Kelvin, and by this latest paper by Okazaki group. Actually, they have seen a switching of Tc, that is, it starts dropping from 25 Kelvin and finally it vanishes at 10.2 Kelvin. Actually, it is a potential candidate because the Debye temperature of diamond is high, and in superconductivity, if you have high Debye temperature, then your transition temperature will be high. But there are some challenges in a diamond growth, because of which the Tc is affected, and we'll also discuss. So this is one of the scenario. One is the boron concentration. What are other factors? If this question is haunting you, then the answer will be coming in the future slides. So my talk was mainly focused on the granularity and its importance. What are the application of having a high granular film? Basically, if we want to define granularity in our films, so if you have laser grains in your films, if the grain size are lower, then at a certain area more number of grains will be there. So we can say this is a high granular film, or the granularity of the sample is high. So as you grow from microcrystalline diamond to nanocrystalline diamond and to alternate crystalline diamond, which is the most highly granular film, your granularity will be higher. And this granularity has an effect on the normal state resistance of the sample, because you have more granularity there, the grain boundary scattering will be higher for the electron and will give rise to more normal state resistivity of the sample, and the kinetic inductance depends on the normal state resistivity. So this is one case. And also penetration depth, that is lambda effective, that is also inversely proportional to the dimension of the grain size. This A is the dimension of the grain size, these grains. So if lower the dimension of the grains, your penetration depth will be higher. And what is the application of having a high kinetic, high penetration depth sample? I will discuss it later. So these are some literature survey where people have shown if you have high level of boron concentration, then you can achieve higher Tc, because higher Tc actually gives rise to the more superconducting density in your sample. Theoretically in BDD, you can achieve 80 Kelvin, that is predicted by some theoretical calculation. But why you need to have solubility limit of 38%, that is not practically possible in a real scenario. Experimentally, what we can achieve is a 2 to 4% of solubility. So having boron concentration just in a manner that you just push the boron flow in a large amount, you will not achieve high critical boron concentration. There are other factors too. So these reports actually show when the grain size becomes smaller and the grain boundaries are increased, the inhomogeneity in the BDD sample will be enlarged. And because of this inhomogeneity, these actually affect the superconducting transition temperature, because this increases the inhomogeneity in the film. So you can see this sample was grown at different time. Basically at different time also your granularity can change. If you do the deposition for a longer time, your grain size also reduce, and you can see for the 20 minutes deposition, your Tc is actually decreases because of the lower grain sizes. This can be actually defined by this parameter, the superconducting density, which actually depends on the superconducting density size 0, but with the granular thing, an exponential factor comes into play. If you have a granularity, this exponential factor will actually decrease the superconducting density exponentially. So in this picture, if you have a same area of your two sample, one is having, let's say, 4 grains, another having 9 grains, you can see easily in the second case the number of grains are higher and the grain boundary contribution is more. Because of this grain boundary contribution, there will be more defects, more basically inhomogeneity in the sample, and your superconductivity transition temperature will decrease. So when the grain boundary area increases, then the scattering between the grains is enlarged and resulting in a reduction of superconducting density. But there is some another report that is a role of grain size in superconducting that was done in boron doped nanocrystalline diamond thin films. Where fascinatingly these people have seen if you increase the methane concentration, we know the grain size decreases. What is the effect on TC? They have seen if you increase the methane concentration, your morphology changes from more lower to nanocrystalline diamond region, but from the boron concentration, this is just seams profile data. You can directly measure the boron concentration, and you can see you can achieve higher level of boron concentration if the methane to hydrogen ratio is high for high granularity sample. And also from the Hall effect measurement, the quasi-particle density that is actually contributing to the transport mechanism, your Hall carrier density also increases with the high methane concentration, and thereby resulting in the high DC. That means more the granularity or lesser the number of lesser the size of the grains, your transition temperature increases. So you can see slowly for the higher granular sample or a higher grain sized sample, I would say, your TC decreases. For a higher granular sample, that is lower grain size, your TC increases. So we have learned that there is a competition between the negative effect of grain boundaries. One is the inhomogeneity, the defect that is affected due to the grain boundaries density. But another way is this grain boundary actually gives an pathways for the boron atom to mix with the diamond lattices to give a higher concentration of boron. You have to achieve higher boron concentration. There is two ways. You increase the boron concentration or you fix the boron concentration at certain flow rate. That is in this case, the boron TMB, that is a trimethyl boron gas we use as a boron source. Thus the flow rate was constant. But with the same flow rate, still we can achieve a higher boron concentration. That is the interesting thing, right? That happens because of the granularity in the flame only. So keeping in that mind, can you still push the granularity? Still we have a superconductivity, but we have a high granular sample to achieve higher kinetic inductance. So if you ask me a question, if the superconducting density if still persists in case of high granular film, this can be explained by a register network model. Basically, if you have two superconducting droplet, if you have a global superconductivity, you have a single crystalline diamond at a particular critical boron concentration, then you can easily achieve superconductivity. That is for sure because your whole sample is superconducting. But if you have islands, certain islands, and that are separated by some distances, individually those islands are superconducting but they cannot give you a global superconductivity unless and until these grains are really close to each other. If it is really close to each other, then a certain physical phenomena happens. That is called the Josephson tangle. Then a superconducting current flows from one grain to the another, and they starts to talking. Then all your grains as a whole, because of this talking to each other, they will give lower some superconductivity. So that is the thing. So you need to have a smaller thickness of grain. You can have lower grain sizes, but your grain boundary thickness should be very smaller. Then only you can achieve superconductivity in ultranionic crystalline diamond. That is one tricky thing because you don't really have control over the thickness of the grain boundaries in the growth kinetics. So the main motivation was new materials with large normal state resistance are needed, and but that do not compromise on the superconducting parameters like the TC, the critical field. Still, those are high. Then that kind of material will be suitable, and this kind of material will retain a low microwave loss properties. If you want to have a microwave transition line, then you can use this material. Then your microwave will flow with less loss properties. Then this also study shows the resonant frequency is extremely sensitive to the superconducting magnetic penetration rate. So this work actually was done in collaboration with this group. The sample was grown in our lab. This was sent to their group, and they have studied the kinetic inductance studies. Basically, they have sandwiched a dielectric spacer between two superconducting diamond samples. On one sample, there is an input antenna from which we can uh, use the input of the microwave, and another part is the output from which we can measure the microwave signal and we can find how much loss is there. So penetration rate also depends on the temperature. It exponentially factor is there, and also it depends on the resonant frequency of the sample. And this penetration rate we have discussed before also. This is inversely proportional to the dimensions of your grains. If you lower grain size, your lambda effective will be higher. Having a high lambda in your sample means we will have lost microwave transition from through our sample. So in this study, boron diamond granular thin film exhibits superconductivity with an optimal critical temperature of 7.2 Kelvin, and such materials will retain low microwave loss properties, which is useful for microwave kinetic inductance detectors, and basically which are the basic building blocks in a quantum impedance devices. In case of qubit, we use single photon detector, and to achieve single photon detector, this microwave kinetic inductor detectors is one of the basic lump sum building blocks. So if you have achieve higher kinetic inductance sample, you can really have a compact microwave resonator, because over a small area of the sample, your kinetic inductance will be high. So you can design more compact microwave resonator, then your chip size will be reduced. So you can achieve highly sensitive photon detectors in that case. This boron doped granular thin film showed a large penetration depth of order of lambda equal to 4.02 micrometer. And if you compare other known materials, you can see this 4.2 release a four order jump, four times, not the four order, it's a four times jumps than the granular aluminum, which is 1.2 micrometer. So the scientific motivation because of those this work, and to have a UNCD superconducting field. Basically, the higher the granularity in the material, higher will be the kinetic inductance, and superconductivity in the bead of UNCD needs to be achieved for this kind of higher kinetic inductance sample. So there is a search for new materials with large state resistances that do not compromise other superconducting properties. Because of this obvious reason, we want to have our cyclicity of lower dimension. We want to achieve higher qubit density over a small dimension, so that we can achieve this supercomputing devices with these qubits. And superconducting BD eventually will serve this purpose. So in the initial stage of my work, I started with a standard sample where it was already reported that if the grain size is 500 to 800 nanometer, that is basically a microcrystalline diamond. With these conditions, I have already discussed that chamber pressure and this methane concentration. So see, I have used a chamber pressure of 6.7 torr only. Lower chamber pressure. I have not used higher chamber pressure. Still, the sample is superconducting, and the sample is in the microcrystalline regime only. So methane concentration is the main factor in controlling the morphology. So I have seen over the temperature range up to 2 Kelvin. I have taken the data of transport studies from the room temperature to up to 140 or 150 Kelvin. There is a metallic behavior, and this sample is quite interesting because you can see at different temperature range, different conduction phenomena is kicking in. There is metallic, there is semiconducting, and also there is superconducting in your sample. And this is the Meissner effect. If you increase the magnetic field, then your TC also decreases because of the London equation, because magnetic field will destroy your superconductivity, and it can be destroyed at 8 to 10 Tesla for our sample. This is the typical orientation of the peak in the polycrystalline diamond thing. We have 111, 220, 311, and 400. This is a signature that this is a diamond sample. For the UN sample, this is the optimized ratio. You have to have 4.5% of methane. That is really crucial. It may vary from chamber to chamber, but for our chamber, it is 4.5%. Chamber pressure is 6 torr, or you can even use 7 torr as well. But as the chamber pressure is low, you need to, yes, you need to have a suitable substrate temperature. Because if it is substrate temperature is less than 750 degrees Celsius, your diamond grow will not happen. The phase will be graphitic. Because at higher temperature, diamond is only stable. And it is a metastable state. So we need to increase the filament temperature. For that we use power supply. We have, I think I have used so far, I remember, 135 volt and 110 ampere. With that you can achieve this filament temperature. So from the crystal Serral formula, this is a rough estimation that the crystal size is order of 10 nanometer, less than 10 nanometer as well. So most of the crystal size is in the regime of 10 nanometer. So this is a ultra nanocrystalline diamond. So this is a Raman spectrum analysis. I have used excitation of about 532 nanometer and a grating of 1800 groups per millimeter for better resolution. And there are 5 certain peaks. These peaks, this is here, which is mainly due to the carbon hydrogen bonding stretching in the grain boundaries and some trans polyacetate, that is CH2 CH in the grain boundaries. Because of this, nu 1 and nu 2 is prominent. And the peak at 1223 is attributed to the sp3 bonded amorphous carbon. This is sp3 bonded, but this is a amorphous carbon, that is because of the graphitic nature of the sample. Also the peaks at 1330 and 1560 are the D and the G band. D peak is the A1G symmetry, that is some nomenclature. This is a symmetric stretching, and there is also G peak is E2G symmetric for in plane bond. So there will be out of plane vibration and there will be in plane vibration. So this sp2 is because of the graphitic, but sp3 bonded is because of the diamond. So this is a diamond structure, but that is not crystalline. This is from the amorphous. Now from the Raman effect, where is the 1332 peak? Because 1332 peak is the fingerprint of the diamond sample. This is there actually in the sample. This is not detected in this wavelength. If you want to really detect that peak, you have to have a laser of less than 300 nanometer in the ultraviolet regime. Then only that peak will be excited. So that is there, but due to the high intensity of the D peak, that is submerged somewhere here. So these are some transport studies on my boron doped ultra nanocrystalline diamond samples. So this coded are use ultra nanocrystalline diamond T20s. I have grown the sample for 20 minutes, 38 at the trimethyl boron gas fluoride. These are different samples, and I have plotted for different samples. The resistivity versus temperature curve is like this. And have you find some absurd in this data? This is not quite usual. You can see there is a step like jump in resistivity with various temperature range. And what I have done is, so this possibly I can see there is 3 regions. So these 3 regions denotes to the 3 temperature modified electronic states near the Fermi level. So at different temperature, different kind of electronic states are excited and they are taking part into the conduction mechanism. So for VRH transport model, log of RT will be linearly proportional to T to the power minus 1 by D plus 1 for 3D, because in 3 dimensions the electron will hop. We use the hopping parameter D equal to 3. So this is not a complex thing. This is just a dependence of resistance, exponential dependence with the temperature. Okay. So you can see from 2 Kelvin to 38 Kelvin, there is another region. From 38 to almost 42 Kelvin, there is 44.6 Kelvin to be more specific, another region, and from 44.6 to 112, there is another region. So different regions, different kind of electronic states are being excited. Because of this, conduction is happening. And all this studies was done only ultra thin samples of 120 nanometer. But if you want to really measure the specific heat, you cannot really do on the really thin films of this 120 nanometer, because you want to have a bulk sample for this kind of measurement. You need a bulk sample. You cannot just put a thin film of 100 nanometer, it will then easily break your specific heat measurement will not go on. So to fulfill that purpose, what I have done, I grow a undoped layer of UNCD. It will give the structural stability of the thin film. On top of that, I grow UNCD for 120 nanometer. This I have done purposefully because all this data actually was obtained 120 nanometer, and I have studied with the increase in thickness, this phenomena is not happening. Maybe there could be some contribution from substrate to thin film interface. There could be those contribution. So what I have studied that, as a from the basic physics we know if there is a superconductivity, there will be a jump in specific heat. From the normal state to superconducting state, there will be a hump-like structure. So at 400 millikelvin, there is a hump-like structure in the specific heat. But as you can see, the percentage change with this point and this point, or at this point, this is not too much high. So I guess this could be a noise in the data. This could not cannot be a superconductivity. This is not a confirmation unless and until we really carry out the transport measurement at those ultra low temperature of millikelvin. So is it really superconducting? I cannot say. Is it not confirmed because of the change in percent of the specific? It is not too much high. So from the AFM data also, if we study the roughness, that is also less than 10 nanometer. Specifically, if the roughness is less than 10 nanometer, your sample is UNCD. So this is also another confirmation from the AFM images. So these are the cross-sectional images. I grow a 15 micrometer of UNCD. Then on top of that, I grow this white part, actually this boron doped diamond. Actually, this part is boron doped diamond sample. If you zoom in, you can see this is almost 150 or 120 nanometer in some cases. So I have more samples I had, which I have not carried out the transport measurement, but I had carried out all those measurements when I visited UECDAE lab in Indore, where actually I have done some fascinating studies. I don't have the data, I cannot show you. I can give an idea. The idea was I had this kind of data and it was repeatable, it was there as well. But as you increase the magnetic field, I have increased the magnetic field up to 12 Tesla. At 12 Tesla, if you increase the magnetic field, these humps slowly actually decreasing. And at 12 Tesla, all these humps fully vanished. Those data I do not have, but that is quite surprising and quite new. It is not reported before in the diamond thin films. That could be reported, because but I have left the PhD, so that work I could not carry it out. That was interesting. I still remember. It is almost 1 year 9 months, but I still remember those data. I was not allowed to take that data because it was not pre-planned that I would leave the PhD. I'll discuss some other day. If you are interested, why I leave the PhD program, because of mainly personal reasons, nothing else. So these are the publication. There are conferences I some attended, some workshops, and also for the beam time. Basically, you can dope diamond with a high moving fast ions that can be achieved in ion implantation. That facility is there at IUSC. We wrote a proposal back in 2000, I guess, 22 or 21, but that proposal was not carried out, though it was accepted during my PhD tenure. So that's it. I have actually given 4 years of my life, 4 years and 2 months to be exactly. I was dedicated enough, and in between the COVID struck in, research hamper, especially in experimental research. If you are far fetched from your lab, far away from your lab, it is very difficult and it is demotivating for you too. But we used to have regular seminars that kept us motivating, but it surely affected with valuable time in our research career. So that's it. So there are some future plan. There are no future plan right now. Unfortunately, I left the PhD program. Now actually, I'm working as a technical assistant at NIT Patna in Applied Physics and Materials Engineering Department, where my job is to carry out BTech lab classes and to operate some instruments. Though we do not have this kind of instrument that I used to have in our research lab, like XPS, we had FESCM, we had XRD, we had Raman, so many and more on. I learned lot of things there. I cannot forget for the rest of my life. Though those are not directly contributing, but if I had an experience certificate, I could have applied for scientist position as well. But I do not have a experience certificate in a proper format, so I do not have a valid experience of those research. So it was not in vain. I have learned lot of things from my lab mates, from my supervisors during the course hour, whoever faculty have taught me. So the main motto to give this talk is because of only me. Far down the line after 10 years, 20 years, if I open my YouTube channel, I could see that I used to have those research days and I gave some seminar. It was a good seminar according to my fellow mates. I don't know how much effort I could give in that day, but surely it took lot of practice. I mean, I you can see I still remember most of the things, I guess. So that's it for today. I'm not regular in YouTube because of studies, classes, office work. But when I feel lonely in my room alone, I make this kind of videos. I hope you learn something. You have some research exposure from my background. Hope this will motivate to go into the experimental research. Thank you for today.